Good evening, this is Mr. Wintermelon. In the previous video, we have learned how to draw genetic diagram and Punnett square. In today's lesson, we are going to learn how to use our genetic diagram and Punnett square to determine sex as well as blood type. So by the end of this lesson, you should be able to describe the determination of sex in human, explain codominant and multiple alleles in the case of our blood group, and explain why the observed ratio is often different from the expected ratio. So first, let's talk about sex, or rather, how your gender is determined. In the previous lesson, we were using alleles, but in this case, we are using the whole sex chromosome. Humans have two sex chromosomes, X and Y. And for us, Y chromosome is the dominant chromosome. So Y will express its phenotype, which is male, in heterozygous scenario. X chromosome will only express itself in homozygous scenario. Phenotype-wise, of course, you need to have a male and female, father and mother. The genotype of male is X as well as Y chromosome. For female, they have XX chromosome. After meiosis, each sperm will either have an X chromosome or a Y chromosome. So 50% of the sperm have X chromosome and 50% of the sperm have Y chromosome. As for female, all their egg have a X chromosome. As for the genotype of the offspring, this sperm can fertilize this egg and the offspring will be XX. This sperm can also fertilize this egg, resulting in XX genotype as well. While this sperm, it's possible for it to fertilize this egg, which will result in XY chromosome, and this egg. So it will be XY. So phenotype-wise, the first two will be female. That means the mother will give birth to a baby girl. While XY, it is a male phenotype. And the ratio of male to female will be 1:1. Which is why the chance of a mother giving birth to a son or a daughter is 50-50. And if anything, the father or the sperm is the one that determines the gender of the offspring. So in the olden days, it might be a bit unfair for the in-laws to be blaming the mother if she wasn't bearing a son or a grandson which they wanted. It is actually 100% the male fault. It is the male or the sperm which determine the gender of the offspring. So this is the expected ratio of male to female. And most of the time we will think that this is true. But is it? So let us check out the gender ratio of these two families. The first family, there are 3 boys and 1 girl. So the ratio seems to be 3:1. While the second family, the parents actually have 3 daughters. So it's like 0:3. So my question is the ratio really 1:1? Some of you might be quick to point out that, oh, Actually, if I add up the two families, there's 3 boys and 4 girls. 3:4 is not bad. It's closer to like 1:1. And actually, you are right. Because if your sample size or the number of children that you are counting is small, then the ratio might not be accurate. Adding up a lot of family will make the ratio closer to 1:1. And remember Mendel experiment? If we take a look at the ratio of the color of the seed as well as the appearance of the seed, you will notice that the ratio is 3.01:1 and 2.96:1 respectively. This is much closer to the ratio of the color of the flower and height of the stem, which is 3.15:1 and 2.84:1. The expected ratio is 3:1. Why is the color and appearance of seed ratio closer to 3:1 as compared to the color of flower and height of stem? Pause for a moment and think about it. The answer is, if you look at the sample size or the number of seed compared to the number of flower and stem that Mendel surveyed, there is quite a big difference. For color and appearance of seed, Mendel was doing in the thousands, while for flower and stem, he was only doing in the hundreds. And this is a good example to show why having a large sample size will help the observed ratio be closer to the expected ratio of 3:1. For all intents and purposes, if they were to ask you why is the observed ratio different from the expected ratio during your O-level, the first answer you should give most of the time is the sample size is too small. Anything below 30 is actually very small. And in the case of Mendel, you can see that even when he was using 100 plus, it is still too small. So this is the default answer that you need to give during your O-level. The second answer which O-level is looking for is ratio figures are based on chance and probability. So the number is unlikely to match. What this means is if you have a son as a first child, it doesn't automatically mean that your second child will be a daughter. The chance of you having a son for your second child is still 50%. So it is really due to chance and probability rather than something that is guaranteed. It is not guaranteed that if you have 2 children, it will be boy and girl. So that's about it for the answer to give for your O-level. Sample size is too small and ratio of figures are based on chance and probability. So the number is unlikely to match. But like I said, is the ratio of male and female really 1:1? We can check the population of the whole world. Now, if you go to the Wikipedia page on list of country by sex ratio, you can actually get all the information that you need. A very big sample size or the whole sample size because we can see information from the whole world. But just take note, the ratio is shown in the form of male is to female. That means if the ratio is more than 1, there are more male than female. If the ratio is less than 1, there are more female than male. And just take note, this is being recorded in the year 2020, so information might change. So if we take a look at the ratio of the world, the total, the ratio is actually 1.01, which is very close to what we want, which is 1. So you might want to jump to the conclusion that, oh, the sample size is large, so the observed ratio is close to the expected ratio. Or is it? Now, if we take a look at the data, we should take a look at the data that is at birth, because this is the data of the offspring. So you can see that, oh, actually for the whole world, the ratio is 1.07. You might not think that it is a lot, but consider Mendel P. It is 3.01, which is much closer to the expected ratio of 3:1. In this case, we are expecting 1:1, but it is not. And considering that the world population is 7.8 billion, this 0.07 is actually not insignificant. The reason why the total is close to 1.01 is because as people age, the percentage of female actually becomes more, especially towards the end. Reason? Because female just have a longer lifespan than male. Maybe because male like to do stupid thing and get themselves killed in war. So female generally have a longer lifespan, which contribute to the ratio that is close to 1 for the total. But at birth, we still cannot deny that the ratio is not equal. And why is this the case? The main contributor or the main culprit for this is two countries. Let's see. It is down here, yes, China, 1.1, and India, also 1.1. And these two countries actually contribute to more than 36% of the world population. So why is country like India and China having such a high population of male being given birth? Not difficult to figure this out, because they value son more than daughter in these two countries. So a very likely scenario is this, especially last time in China when there's a one-child policy, which could explain why over here the male is even more. So back to when a wife is pregnant. When a wife is pregnant and they went to do a scan and it is a girl, maybe the family can choose to abort the fetus. So in countries like China and India, they might prefer a male child. So they will selectively choose to give birth to a male child. How do they selectively give birth? By getting pregnant until they get a male child. So selection pressure, in this case human preference, can also affect the observed ratio. And this can easily cause the observed ratio to differ from the expected ratio. So as you can see, human selection can play a role in determining the final outcome of the ratio of male is to female. It could be the same for some other phenotype. So selection pressure might affect the fitness of the allele or the gender. Fitness is another way of saying the number. The example which I have given is the family might opt for an abortion if the gender of the child or the fetus isn't what they wanted. So this kind of selection pressure or preference might affect the observed ratio. Speaking of selection pressure, let us revisit Huntington disease. What is the probability of getting Huntington disease? Let us draw some Punnett square to find out. So let's say you have two homozygous individuals. One is homozygous dominant and one is homozygous recessive. What will be the outcome? The outcome is actually 100% of their kids will have the disease, then you might be thinking, if the probability is 100%, maybe the parents wouldn't want to have a child. And yes, you are right. But the symptoms of Huntington disease normally begin between the age of 30 and 50. Although it can start at any age, only 8% started below the age of 20. So a person might not know whether he or she has the Huntington disease and might reproduce before the age of 30. So this is why even though Huntington disease is caused by a dominant allele, the patient might still have offspring. Now, if we look at the second Punnett square, whereby we have a heterozygous individual and a homozygous recessive individual, you can pause the video and do the Punnett square and see what is the probability of the offspring having the disease. And you should get 50%. And please carry on with the practice for the next example. Pause the video and do this Punnett square, whereby we have two heterozygous individuals. These two heterozygous parents will suffer from this Huntington disease. How about their kids? Their kids will have 75% chance of getting the disease. So please check whether your answer is correct or not. Because 3/4 of them will have at least one dominant allele. And it is only when the two parents have two recessive alleles that the chance of getting the disease is 0. So as you can see, the chance of someone having Huntington disease is kind of high. However, the disease only affects 0.0075% of the world population. Why is this the case? One possible reason is while symptoms normally begins between 30 and 50 years old, it might start earlier and the person might opt not to reproduce. Or when a person found out that his or her parents have this disease, he or she might choose not to reproduce. So this is some kind of selection pressure. So even though this allele might be dominant alleles, but having this condition will affect the reproductive success of an individual, which is why we do not see over 50% of the population having this disease. Another reason is just could be the starting population size is not as big. And of course, having a small starting number of people with these alleles also prevented this disease from becoming very common. So besides small sample size, ratio are based on chance and probability as well as selection pressure, some phenotypes also have a negative impact on the survival as well as reproductive success of an individual. So these last two reasons are also possible explanation as to why the observed ratio differs from the expected ratio. But for all intents and purposes, try to write the first two reasons as the answer for your O-level. Because the last two answers could be situation specific. Lastly, let's go back to our blood group, whereby there are multiple alleles, specifically A, B, and O. But just take note, for other genes, right, we just use a single letter. In the case of blood group, please use I followed by a superscript A, B, or O to represent the alleles for blood group. This is the specification given by Cambridge. Why is it important? Because it will help to differentiate genotype and phenotype. So IO, or the O alleles, is recessive to A and B. So you can pause the video and try to figure out the phenotype of the following genotype. For the first genotype, the phenotype is O. So you can see why it is important for us to write the genotype as IO. It will help to differentiate genotype from the phenotype, which is unlike color, whereby let's say yellow we use capital Y, then the phenotype we spell it out as yellow. For our blood group, the genotype have to be differently written from the phenotype to avoid confusion. The second phenotype is A, third is B, fourth is A, fifth is B. The last one is something special, which I mentioned before. The phenotype is AB. So in this case, it is known as co-dominance. Co-dominance is situation whereby there are two alleles controlling a trait, in this case, your blood group, both expressing themselves. That means those two genes, they are like producing the protein at the same time, which is unlike your dominant and recessive, whereby the dominant alleles is most likely producing a protein, while the recessive alleles is not producing a protein. So it will give the dominant trait. So the dominant alleles will express its phenotype. So this is co-dominance. Then there is also incomplete dominance. So in the case where intermediate trait is being expressed, for example, if you have a white color mouse, you breed it with a black color mouse, you get the offspring with gray color fur. That means the color between black and white. So this is just to take note, not spelled out in your syllabus. They are similar to co-dominance, but different at the same time. They are similar in the sense that both alleles are expressing themselves, but different at the same time because the phenotype is different from the both of the original. So this incomplete dominance, I would say, is good to know there's such a thing. So lastly, let us practice our Punnett square again on these three crosses. And let me just remind all of you, in exam, do not be afraid to draw Punnett square for your MCQ. Do not just use your mental calculation. Draw a Punnett square to help you figure out. And of course, find out the ratio of phenotype of offspring. So pause the video and go try it out. When you are ready, unpause now, and I will tell you the answer. So please check whether your answer is correct. Please make sure that for your genotype, you must have the I down there. So the phenotype of blood group A and B will be 1:1 for the first case. For the second case, all of them will be blood group AB. And for the third, we will actually have three blood group. Blood group A, it will be 50% of the offspring might have blood group A. Take note, I use the word might have instead of will have, because this thing is based on chance and probability. 25% chance of having blood group B, as well as 25% chance of having blood group AB. So this will be all for all the genetic diagram and Punnett square practice. So this will be the end of the two-part lesson on genetic diagram as well as Punnett square.